it is really a great honor and very humbling experience, to be here, because I am among friends. I'm really among friends, friends of, you say 40 years. I didn't count because it's so many years, but it's great. And I remember vividly the nice time I had here during my sabbatical. And I have to say that some of the, that was 20 years ago, more. I have to say that some of the work, the idea, and so on, that I'm going to present here, they in fact, were born here. But it took about, 10, 20 years to develop and so on. But they were really born here. I was talking with Horatio, I was talking to Sandro, I was talking, and so, I mean, this place for me really is very important. And I'm really very, very honored, to accept, of course, this honorate degree, and from this university. And I can assure you that it's not the end of it. I wouldn't say it's not the beginning because we have, but it's far from being the end of it, because I believe very, very immensely to the field of ultra short and ultra intense field. And I think that the new engineering class, that, I think they made a good choice. They made a good choice. Okay, so I guess I'm going maybe to start my presentations. And I cannot start my presentation without introducing my former grad student and also my co-laureate, Donna Strickland. Okay, it is with Donna that we developed this concept of chirp pulse amplifications, and it was great. So, of course, it's a laser, okay? It's about laser. And also, we cannot talk about laser without evoking, Ted Maiman, okay? But you can see, who really showed clearly the first laser, the first generation, I have to say, because laser is just a generator of coherent light. The light was 14 billion years old, or about. And, but it's only 60 years ago that we were able to fabricate coherent light. Okay, and that was thanks to Ted Maiman. So, and what is fascinating about lasers? The lasers, really can do so much. I'm going to try to help you to understand that. The first thing is, for instance, if you take the light coming from a laser, okay, you can use it to slow down atoms. Slow atoms move at about 300 meters per second, and room temperature and so on. But you can take the light, and I'm going to tell you how to do that, but it was in fact, the technique was inspired by Art Ashking, which was also a co-laureate. But anyway, so you can slow down almost to a stop, the atoms, for instance. And you can, and many, this one is now that's a very important field, which is called the quantum optics field. In fact, something which is very closely related to the past, the recent Nobel laureate, like aspect, and so on. So, but the other thing that we can do, so we can really cool down atoms. And the other things that we can do just the converse. We can accelerate atoms to all the other limits, which is the speed of light. So we can go to 0 to the speed of light just by using the laser light. Okay. So, and that gives you, an idea of what you can do with light. Now, I mean, the shear-pulse amplification, I'm not going to describe it because I think Professor Svelto did a very good job, and I'm not going to be able to do better than that. But right now, it is what is, so we now with CPA, we can produce very, very intense light, okay? And, but also, we can produce a very intense light, but we can produce also with the same light, the largest peak power, the largest temperature, the largest pressure, the largest accelerations, the largest field. And it is really a universal source of high energy particle and radiations. It's phenomenal, and you will see now some of the information, the applications. First of all, this is my curve, which is producing on the ordinates, intensity, that is watt per square centimeters, as a function of time. Okay, so when Ted Mayman invented the laser, we were talking about intensities in 10 to the 8 watt per square centimeter, and so that was the best we could do at that time. Laser was invented, and then when we came with Donab, with his CPA technique, that was in 1985. So you see that we had this big plateau in intensity that we couldn't really overcome, and we had to stay at 10 to the 14 watt per square centimeter because the intensity at that time, after that, you were kind of destroying, your laser component, and your professor was not very happy because it was costly. And then after that, when we got the CPA, then we could get into, very high, much different intensity regimes. And right now, and this is what I'm going to focus on, is we can really go into intensity in a range of 10 to the 23, 10 to the 24, these limits. But what we want to do, really, this is not enough for us, although it's already very, very high. We would like to go into the regime where the light is so intense that if we focus the light in vacuum, we can produce matter. Okay, so we can materialize light, and we can materialize vacuum. So this is what I'm going to talk about, and some of the applications. So because we have now incredibly powerful light, there's one thing that we can do, and which is going to be a game changer. It is the fact that we are going to leave the atomic physics realm where really optics is. Optics is, the regime of electron volt, okay? And now we are going to, because we have these very, very high intensities now, we are going to go into a subatomic regime, okay, where we are leaving the realm of molecules and atoms to go into now subatomics where we are going to use the nucleus and the components, of nucleus. So this is what we can do with now light, okay? And I have to say that some of the idea emerged in my mind when I was here in Milano, during my sabbatical time. And so we moved from the electron volt to the tera-electron volt, okay? So now, how can we do that? How can we do, okay, I'm going to go back, sorry. So as I said, we were in a regime of materialization of light and so on. That is the highest point we can achieve. But now, we would like, as I said, we would like to go into the materialization of light. And how can we do that? We have to increase the power. So there is two ways. The power is energy divided by times. So there is two ways to do it. The first way is to increase the energy of your laser, okay? And the second way is to decrease the pulse durations. So increasing the energy is expensive. It's very, very expensive. So if you want to increase the energy by a factor 100, thousands, and so on, the type of increase we are talking about is going to be very expensive for you. So the other things, and this is what the idea came after Professor Svelto and his group demonstrated this compressing idea, but he didn't have the time really to tell you. I say, well, we should really use that, but not at the millijoule level, but trying to go much higher at the joule level. But basically using the same idea. So so the idea was trying to compress the pulse. That is, we produce a short pulse from the CPA, and then when it's done, we are going to try to compress it again, okay? And we want to improve by a factor 1,000, maybe 10,000 the peak power. That means we have to compress the pulse by a factor 1,000 and maybe 10,000. And this is what we are after. And of course, that's going to change the field. So the idea is to take the short pulse, 20 femtosecond typically, and 20 femtosecond is about, we're talking about electromagnetic wave. And 20 femtosecond is about 10 optical wave like this, 10 cycle, okay? And we would like first, we would like really to compress it in one cycle, okay? That's the first job. And the idea came from Professor Svelto's group, and is using a capillary. I have to make it, I'm taking some shortcuts here, but capillaries. And if you go in this lab, you will see a lot of capillaries. And what you do is you are piping the laser into this capillary, and this capillary is filled with noble gases, and you are going to change the index of refractions of this noble gas during the laser pulse. That's very important because that is going to lead to some what we call cell phase modulation, and that's going to broaden the spectrum. And you know that if you want to shorten a pulse, you have to broaden these spectrums, okay? So this is what you do. And this technique was really invented by Orazio Svelto and his group. But now, this was good for millijoule pulses, and we want really to go to much higher. So we have to compress now joule pulse, pulse with energy of the order of joule or maybe more. So we can go much higher. And so what we do is, because now we are going to use still laser with a lot of energy, and a laser with a lot of energy, usually for the people who are going to work on laser, has what we call a flat top. Okay, you see that here is the intensity as a function of space. Here you have a flat top here. Okay, if you are at a modest amount of energy, you are going to have a Gaussian pulse, right? Okay, and so you want to go to the Gaussian, to flat top, and this is what you get when you buy a pulse of high energy. So now what you are going to do is, instead of using a capillary, okay, you are going to sorry. Again, yeah, okay. You are going to use something very, very thin, like thin film, you know, which is uniform over 2 dimensions, okay? And so you will be able, right, to come up with laser pulse and use a thin film, so you are going to really change the index of refraction over a relatively large area. I'm not going to go into detail, I don't have any time, and then when you change the index of refraction across the beam, then you compress it and you get pulses shortened quite a bit to almost a single cycle. I have a trouble with, I cannot switch. It works? Doesn't work. No, it's not working. Maybe. Where should I? Stay with me. Okay. So anyway, once you have broadened the spectrum of your pulse, then you compress it, and the idea you should be able to produce one single cycle. Okay, but so what you have done is you just gain a factor of 10. Okay, you went from 20 femtosecond to 2 femtosecond, so it's not enough for what we want to do. What we now we came up with an idea, which in fact also I described it when I was at taking my sabbatical here. The idea of relativistic compressions. And here you see this single cycle that I just showed you, okay? Single cycle here. And now this single has a lot of energy, so the intensity is very large. So you can focus the beam on a target, which is composed, of course, of electrons and protons and so on. And then you are going to focus it. And what happened is, because this pulse, you know, it can push, I told you, but we can generate the highest pressure with a high intensity pulse, okay? And we are going to press this we are going to move these electrons a great deal. You see, but where we press it, we move the electrons, but the ions, which are more massive, stay behind. So what you are going to do is you are going to basically make a quasi steady electric field, okay? Quasi DC electric field, okay? And so now once you have that, but the field is so large that is going to move the electrons this way, this way. So the net result is you made basically a relativistic mirror, a mirror which is moving at the speed of light. Think about that, okay? When you look, when you're shaving yourself, you can see if the mirror was coming to you at the speed of light, okay? Anyway, and when you do that, this translates into compressions. You are compressing the pulse, okay? And the compression is pretty large, and it is basically equal to 600 attoseconds, 10 minus 18 seconds, divided by the field. I'm not going to go into the details. So now you can really, you have the hope to compress the pulse to attosecond, sub-attosecond, and if you're optimistic like me, we can really see zeptosecond. Zeptosecond is 10 minus 21. Why do you want to do that? Zeptosecond, you see, is great. I mean, if you produce a pulse with a zeptosecond and 1 joule zeptosecond, what you have a zeta watt laser, 10 to the 21 watt, okay? 10 to 21 watts, if you take electric power plant, a power plant, a gigawatt, you see that is about 10 to the, it's 1,000 times billions of watts. Power plants. And so this is the type of thing. So of course, if you're focusing this beam over the wavelength, then you get intensity of 10 to the 21, 10 to the 29 watt per square centimeter. This is what we call the Schwinger intensities. Is where you can start to produce matter out of nothing, okay? Okay, and so you can really produce this way. I'm going to switch, move fast. We can produce particles and we can accelerate particles very, very violently and on a small scale. So now let's talk about low-hanging fruits, okay? Because when you are doing experiments, also you have to keep in mind about what you could do with them. And so, first of all, we can now produce very high energy protons. So now, why do we want to produce high energy protons? This is a weird idea, right? You will see the applications are immense. Let me show you that. And so how we can produce short bursts of protons? Very simply, we have our very high intensity pulses, single cycle and so on. And then we can produce, we whack the pulse on very thin films, okay, of nanometer thickness, and we can produce, the electrons are pushed forward, the ions are left behind, and you can produce protons. In fact, the protons that you produce are very high, have very high energies. They are in GeV, they are relativistic. This is immense because if you want to do that with a system, let me show you first. So, with a single, I'm going just to jump. So if you want really to, here what we propose is really to produce GeV protons over in a compact way, okay? This is what I described. And if you want to do that with conventional systems, this is a type of system that you need, kilometers long, okay? to be able really to accelerate protons to the GeV regime. Kilometer long. I don't, so you can imagine the cost, okay, of this instrument. And so now, why do we want to have protons of this energy, of this relativistic protons? And because you can use it, for hadron therapy, for instance. Hadron therapy, where you have, you can focus a beam on, if you have a tumor of a patient, you can only with hadrons. What you want to do, hadrons and not electrons, not X-rays, is because with hadrons have a properties not to affect, you can affect only the tumor and not the healthy tissues around the tumors, of course. And so this is the type of things you want. Then you can do also nuclear therapy and nuclear diagnostics and so on. I'm going to switch now. But what you can do, and I'm very, very excited about this, is the fact that we could maybe be able really to produce abundant and clean nuclear energy. And that, I think, is, of course, is the biggest problem that we have in our society now. How can we produce energy clean and abundant? Okay? So you can use, in fact, these protons to produce what we call neutrons, okay? And then, if you have these neutrons, you can really now, of course, you can produce, you can use them to application like, alors, I'm going to do that. Yeah. Application like transmutations. We know that when we are producing with nuclear, for nuclear energy, when we are producing power using fission, okay, what you are before producing with energy productions, you can produce minor actinide. And these are these minor actinide which are really the problem, okay, for nuclear energy. Another thing is also if you have neutrons, what you can use the neutrons to use thorium. So let's see. Let me show you. You have uranium and thorium are two elements, which are in fact from the same category, and that you can use. Okay. Now we made a choice, some time ago, to go for uranium and not thorium, but I think we could look at thorium again. But anyway, just to give you an idea, if you are talking about why do you want really to use nuclear energy, well, if you if you have a 1 gigawatt power plant, okay. If you want to produce this gigawatt, for a year, it will take you 100 trains or 10,000 wagon, okay, of gold, 3 million tons of gold, and of course a zillion amount of carbon dioxide. Now, this is if you are using a coal, but if you are using uranium, it's only 300 tons of uranium and 0 liter, or virtually none amount of carbon dioxide. But now if you go from uranium and you go to thorium, then it's much better. Oops. You need only not 300 tons, but you will need only 1 ton of thorium, and you will, of course, not produce carbon dioxide. What's nice about thorium, there is pros and cons, of course, and we can talk about if you are interested. but it is also the amount of what we minor actinide, which are really the bad guys, that you are producing is much less. Okay. Let's see now. Yeah. You know, fissions, when you have our neutrons, remember neutrons that we have produced now? So we could use these neutrons, you know, to do fissions and produce energy. And when you send neutrons to nucleus, like uranium or thorium, then you are going to really fragment, and that's called fission. You are going to fission the nucleus, and you are going to produce, you know, you are going to produce new elements. Okay, these elements are okay, you know, they don't live very, very long and so on, so they are not a problem. But some of the neutrons, you are not just going to fission, which is okay, but what you are going to do is some of the neutrons are going to be captured by this nucleus, and you are going to make what we call minor actinides. And these minor actinides, which are really the problems, okay, because they are very long lifetimes. And these are the problems with, the main problem with fissions. So now I have my neutrons that I can produce with my lasers and so on. And with neutrons, you know, we can do two things. We can produce fissions and produce energy, but also we can treat minor actinide. The minor actinide can be also blasted with neutrons, and you are making some new elements, but elements with much shorter lifetimes, okay, like hours or days or things like this, which of course are, would be incredible if we could do that. Now, just I may want, maybe I should stop here. What do you think? I have a few slides about what we can do with short pulses. You can go? Okay. Yeah, I'm going to finish, you know. Is one of the problems that we have, our society has, is to clean the space of all the millions of debris that we are produced as we are really launching, you know, satellites and so on. And you know that now we have millions of debris, and we have to remove them. We have to clean them because they are very, some are very big, like a washing machine, and some are very small, like millimeter side, centimeter side. So, but they are still very dangerous because they fly at 10 times the speed of the fastest bullet, okay? So even if they are small, they can be very harmful, okay? So how could we really get rid of them? Well, I mean, we can embark one of our lasers, short pulse lasers, you know, in a capsule, and then we can aim. So this is very interesting. Oh yeah, the amount of stuff that we have sent into space right now is something like 28 million tons, which corresponds to 4 Eiffel Tower. Okay, that's the amount of space since the beginning of the spatial ages. And there's about half an Eiffel Tower which is going around, okay? And so what we want to do is we get rid of these debris, and the way we want to do that, we are not going to trying to explode these debris, you know, by aiming our short pulse to the debris like we do here. But what we are going to do, we are going to generate, ablate with the laser, a little part of the debris, and this ablation is going to produce a rocket effect, and so the debris is going to be deorbit and fall in the atmosphere. And this is what we would like to do. This, of course, you need a special kind of laser to do that, and this is a laser. I'm not done the time to describe it. You see that this laser is special because it's composed of optical fibers. Okay? This is optical fiber. It is a way, really, to produce not only high peak power, but very high average power and repetition rate and so on. The type of things that we need to do the job. Well, when you're Nobel Prize, sometimes you can be invited, by very high up people like the Pope. I'm sorry.
Not like us today.
Maybe he's going to visit the lab and say, yes, you have to do what you are doing. That is short pulses, high intensity pulses, because as Mourou said, you are going to clean the planets and so on. So we are with Donna and myself, and we had the chance to spend about 20 minutes with the Pope, and we told him, what are you doing? Well, what we want to do is to trying to produce energy, abundant and clean. And also, by the way, we would like to clean the space around the Earth. And he said, wow, great. Keep going. And I think I'm going to stop here by concluding. I say that extreme light, where you are so good here, is capable of generating the largest field, the largest acceleration, the largest temperature, and the largest pressure, and it carries the best hope and opportunity for the future of science and society. Basically, this is what the motto of Nobel, So thank you very much.